Welcome to the lecture series again. Today I will be talking to you about the chemistry of group 2 elements, that is alkaline earth elements. They are also called S2 block elements. Since they have 2 electrons in their valence shell, they are called S block elements as well as S2 block elements. And you know the electronic configuration of alkaline earth elements is NS2. That means they have 2 electrons in their valence shell, and hence the group oxidation state of alkaline earth metals or alkaline earth elements is +2. Beryllium, the first one, next magnesium, calcium, strontium, barium and radium. Of course, radium is radioactive, and similar to lithium among group 1 elements, beryllium differs from other elements owing to its smaller size and very high charge to size ratio, but beryllium resembles more of aluminum. That means it has a diagonal relationship with aluminum. At the end, I will be discussing about the diagonal relationship and similarities between beryllium and aluminum, and atomic and ionic radii are smaller than those of group 1 elements, because here they have 2 electrons are there, and also there is an increment in the effective nuclear charge. As a result, what happens? The size shrinks. Okay. So, atomic and ionic radii are smaller and they readily form M2 plus ions. The cationic species can be done readily by removing 2 electrons, and M plus ions and M2 plus ions. If you compare between alkali metals and alkaline earth metals, M2 plus ions are smaller than M plus the alkaline earth elements in their free state. Atomic and ionic radii decreases down the group as the size increases. Again, similarities are there between alkali metals and alkaline earth metals, and ionization enthalpies decreases down the group, of course due to the increase in the size. The first ionization enthalpies are higher than those of the corresponding group 1 elements, and here second ionization enthalpies are lower than the first ionization enthalpies, because in the case of first ionization enthalpy you have to remove electron from a paired set, that is S2. Okay. Obviously, it requires larger energy, and once after removing one electron, removal of the second electron would be lot easier. That is the reason the second ionization energy or ionization enthalpy is much lower compared to the first ionization enthalpy. And again, when you compare hydration enthalpy, the same trends are followed. Hydration enthalpy decreases down the group due to increase in ionic size. The sequence that followed is very similar to alkali metals. Hydration enthalpy is highest for beryllium and then magnesium and then calcium, strontium. So, this is the sequence that is followed as far as hydration enthalpy is concerned. And due to the larger size, group 2 elements are more extensively hydrated compared to group 1 elements. Example, magnesium chloride. So, due to the larger size of alkaline earth metals, they are more extensively hydrated compared to group 1 elements. Example, magnesium chloride is hexahydrated. If you recall lithium chloride, that is dihydrated, that means it has 2 molecules of solvated water, whereas magnesium chloride has 6 molecules of solvated water, and same thing is true with calcium also. If you compare those with sodium and potassium chlorides, they do not form such hydrates, and all these alkaline earth metals are silvery white in color, and they are soft but harder than group 1 elements, and again they are all strongly electropositive, and this electropositivity trend increases down the group. And chemical reactivity of group 2 elements can be again considered by looking into their interactions with air, that is water, oxygen, hydrogen, nitrogen, halogens, and also its reducing capability, and also its behavior in liquid ammonia, and also its interaction with organic moieties. And if you see again, it imparts colors to the oxidizing flame. For example, beryllium and magnesium do not impart any color because of the high ionization energy associated with them, whereas in case of calcium it gives brick red color, and in case of strontium it is crimson red color, and whereas barium gives characteristic apple green color, and the corresponding wavelengths are given here 662, 650 and 554.5 nanometers respectively for these emissions. And in this case the emission is a result of the electron excited from, so we have NS2 electronic configuration. So, when the S electron is excited, we have a electronic configuration of NS1, NP1 electronic configuration. That means, one of the S electrons is promoted to P1. As a result, the intense color is observed. When this electron returns to the ground state, okay, they emit the radiation in the following region. This is how the color will be seen. And when we look into the reactivity, you can see the flame test colors here. Very nice apple green color can be seen in case of barium and strontium, and calcium the corresponding colors. Of course, because of these nice colors, they are also used in firework. Let us look into the chemical reactivity of group 2 elements, and because of smaller size compared to alkali metals, they are strongly hydrated. That we saw in our previous slide, that is magnesium and calcium are hexahydrated, having 6 equivalents of water molecules, and they also have high lattice energy, and beryllium has a different chemistry compared to magnesium, calcium, strontium, barium and radium, and free beryllium 2 plus does not exist unlike other alkaline earth metals, and always its compounds are covalent and contain solvented ions such as when you put sodium chloride or potassium chloride into water, you can see Na plus ions and Cl minus ions, whereas in case of beryllium that is not going to happen, and instead it always exists as a coordinated complex having this kind of formulation. Many of the salts are less soluble in water. For example, K2SO4 is soluble, not calcium sulphate or strontium sulphate, and beryllium is a rare element, okay, and that is extracted from this ore called beryl. It has the composition Be3Al2 Si6O18. So, I briefly discuss about the extraction of beryllium from this ore. First, it has to be treated with sodium hexafluorosilicate, that leads to the formation of a fluorinated compound having formula Na2BeF4. This one on treatment with sodium hydroxide forms beryllium hydroxide, Beryllium hydroxide, when treated with ammonium hydrogen difluoride, a very strong fluorinating agent, it forms NH4 twice BF4, from which one can get BeF2 simply by heating. Once after getting pure beryllium fluoride, it can be reduced using magnesium to get elemental beryllium. So, this is how beryllium is extracted from beryl, and simple anhydrous compounds of beryllium are covalent in nature. When crystallized from water, as I said, salts are formed like hexa aqua beryllium 2 plus are formed. Hydrated beryllium ion, that is tetra aqua beryllium 2 plus, is very similar to hydrated aluminum and both are acidic in nature as a result of high polarizing power of the small highly charged beryllium 2 plus ion, which results in hydrolysis. The other hydrated group 2 cations are not acidic owing to their lower charge densities. For example, if you take it gives BeOH H2O 3 times plus H3O. So, therefore, what you can call as tetra aqua beryllium 2 plus only exists in strong acid solutions. On increasing the pH, hydroxide bridged ions such as BeOH3 So, on increasing the pH, hydroxide bridged ions such as BeOH3 whole thrice will form, and eventually that leads to the formation of BeOH twice. In excess hydroxide, BeO and BeOH twice dissolve to give berylite ion, that is BeH2O4 2 plus, demonstrating the amphoteric nature of beryllium. This trimeric structure will appear like this. So, this indicates the amphoteric nature of beryllium, very similar to aluminum hydroxide. And combustion of group 2 metals in oxygen gives monooxide species like strontium oxide, barium oxide will absorb oxygen under pressure to give peroxides. That means, under normal circumstances all of them will form monooxides, but only in case of strontium and barium under high pressure one can prepare the corresponding peroxides MO2. peroxides and superoxides are not formed by combustion and tend to be unstable because the smaller M2 plus ions are highly polarizing and cause the peroxide and superoxide salts to decompose to MO, which have high lattice energies. So, you can see here the lattice energy is in the close to, in case of beryllium oxide it is minus 4298 kilojoules per mole. In case of magnesium oxide it is 3800 kilojoules per mole, and in case of calcium oxide it is 3419 kilojoules per mole. Strontium oxide it is 3222, whereas in case of barium it is, so it is steadily decreasing. Nevertheless, they show very high lattice energies, and also that is also reflected in the melting point. If you see the melting point, case of beryllium oxide is 2500, whereas that drops to about 1475 in case of barium oxide. And this calcium hydroxide, it can react with hydrogen peroxide and water to form calcium oxide. So, calcium hydroxide reacts with hydrogen peroxide, aqueous hydrogen peroxide to form calcium peroxide, and calcium oxide itself, when treated with water, forms the calcium hydroxide. And similarly, magnesium 2 plus reacts with hydroxides to form corresponding magnesium hydroxide. And barium hydroxide is the most stable and most soluble hydroxide among all hydroxides of group 2 elements. And the carboxylate salts of the metals magnesium to barium of the type all normal salts okay. However, beryllium hydroxide reacts with carboxylates to give basic carboxylates. So, basic carboxylates have the formula Be4O, 6 carboxylate groups are there. That means there is a difference in the reactivity with carboxylates. With magnesium to barium, you get simply corresponding carboxylates as normal salts similar to palladium acetate, sodium acetate. Whereas in case of beryllium hydroxide, it reacts to give a basic carboxylate which has 4 beryllium atoms, 1 oxygen atoms, and 6 carboxylate groups are there. And let us look into the structure, how it looks. So, you can see here oxygen is coordinated to 4 beryllium atoms sitting at the center of the tetrahedron, and now these carboxylate groups are essentially bridging ligands. What they do is they bridge in this fashion to stabilize this tetrahedral beryllium moiety. If you just look into the acetate group, this is something like this. So, this comfortably bridges as a monoanionic ligand. So, we have 6 such carboxylate groups, they are bridging beryllium atoms to give this structure to basic carboxylate. Lead also forms similar basic carboxylate, and magnesium reacts with nitrogen on heating to form magnesium nitride. And of course, magnesium nitride is very reactive. On treatment with water, it undergoes hydrolysis, very similar to lithium nitride, to form ammonia and magnesium hydroxide. And group 2 metals dissolve in liquid ammonia to form blue solutions containing solvated electrons similar to alkali metals. However, their solubilities are much lower. All of the group 2 metals except beryllium form an ionic dihydride MH2 on heating the metal in hydrogen. Because of high ionization energy associated with beryllium, it does not react. As a result, using simple method, one cannot make beryllium dihydride. Instead, one has to go for drastic conditions. For example, beryllium hydride can be prepared starting from beryllium chloride, which on interaction with lithium aluminum hydride gives So, this is one method, and if you want to prepare very pure beryllium hydride, there is an indirect method is there. In this one has to make first a tributyl beryllium compound, that is beryllium chloride has to be treated with Grignard reagent such as tertiary butyl magnesium chloride. This gives initially ditertiary butyl beryllium plus two equivalents of magnesium chloride. Ditertiary butyl beryllium on heating, it forms beryllium hydride plus two equivalents of propene. So, you may be wondering how ditertiary butyl beryllium compound gives beryllium hydride plus two equivalents of propene. Basically, what happens when you have some beta hydrogen atoms, they have a easy pathway for decomposition, and one such mechanism can be seen here, that is called beta hydrogen elimination. Just if you look into the slide I have shown here, you can see here this is we have an ethyl group on metal, and this ethyl group or some organic group having beta hydrogen can be written in this fashion. When you write in this fashion, you can see this is the beta hydrogen atom, and due to this coming very close to metal, you have this 4-membered intermediate here, and this intermediate takes hydrogen onto metal and formation of ethylene is seen, and this ethylene bond bridges and eventually this decomposes to give metal hydride and an alkene is formed. So, this is essentially the decomposition. Pure beryllium hydride can be prepared starting from ditertiary butyl beryllium. Okay. Using beta hydrogen elimination method. For example, here let me show for the formation of one beryllium hydrogen bond, the same can be repeated with another one. Let me write in this fashion. As I had mentioned earlier, it forms a 4-membered ring, and then eventually this bond breaks here and this bond breaks here, leading to the formation of plus so here 2-methyl propene is formed. Similarly, this tertiary butyl group also undergoes beta hydrogen elimination to form this, again undergoes another beta hydrogen elimination to form H2. So, here one more, this group is formed here. And reactions with halogens are very similar to alkali metals. Directly one can react with halogens to prepare the corresponding MX2 species. Okay. And thermal decomposition of dibutyl beryllium tetrafluoride is the best method for the preparation of BeF2 that I showed you while showing the metallurgical extraction of beryllium from beryllium ore beryl. So, if you take here, one can get pure beryllium difluoride. One can also prepare using carbon reduction using beryllium oxide . Of course, this reaction happens only at a temperature of 600 to 800 Kelvin. And BeCl2, beryllium dichloride, is a covalent polymer in the solid state. Anhydrous beryllium halides are soluble in many solvents owing to the formation of complexes. Other alkaline earth metal chlorides such as magnesium chloride, calcium chloride, strontium and barium chloride are ionic water soluble salts, but fluorides are only slightly water soluble owing to the high lattice energy for M2 plus ion and small F minus ion. In fact, that is true with most of the fluorides, whether we consider sodium fluoride or in general alkali metal fluorides or alkaline earth metal fluorides or even aluminum fluorides, they are all having high lattice energy owing to the same charged cations and small F minus ions. Let us look into further chemical reactivity. As I said, your calcium chloride has FCC structure. One can see from this one. And this is very similar to sodium chloride structure. In case of beryllium chloride, it has polymeric structure. Why it has polymeric structure? Okay, in solid state, it has a polymeric structure with two chlorides bridging the adjacent beryllium atoms, so that you have a spirocyclic beryllium continues in one dimension, leading to the formation of a polymeric chain. Whereas in case of gas phase, it exists as both monomeric form, that is BeCl2, and also dimeric form Be2Cl2. The sulfates are also known. Solubility of these sulfates of alkaline earth metals decreases going from beryllium to barium and all the group 2 metal sulfates lose SO3 to form the oxide on strong heating. If you take a typical alkaline earth metal sulfate, on heating it forms the oxide plus SO3 is released. This is very similar to carbonates giving the oxide plus carbon dioxide. This is true in case of magnesium, calcium and strontium. And whereas barium carbonate is much stable to heat and it does not decompose readily, and in liquid ammonia alkaline earth metals dissolve to give deep blue color solution similar to alkali metals. Again this is very similar to alkali metals in liquid ammonia. So, here the color is more intense, it is essentially because of this kind of reaction that happens. So, it forms two kinds of complex ions. So, here due to the presence of divalent cation surrounded by ammonia and also electron free electron surrounded by ammonia, you have two sets of complexes in liquid ammonia. With carbon one can make different types of carbides. For example, magnesium, calcium, strontium and barium form ethanides, that means acetylides when treated with acetylene, and to make compounds of the type MC2. Okay. So, essentially if you look into this formula, it appears like C2 2 minus ion is present. Example, calcium carbide. Beryllium and magnesium also form two other type of carbides. So, beryllium on direct combination with carbon forms beryllium carbide at high temperature. And in this case, okay, in most of these carbides of highly electropositive elements, on hydrolysis the corresponding hydrocarbon is liberated, whereas in this case beryllium carbide on hydrolysis it gives methane. And another carbide is Mg2C3, or it can also be written in this fashion. And of course, beryllium carbide has this so this is how you can satisfy the valency and write the correct structure. Okay. The most important organometallic compounds of group 2 metals are the Grignard reagents. Grignard reagents are simply prepared by treating alkyl halides with magnesium in a polar solvent such as ether. Okay. So, this Grignard reagent or RMgCl are always solvated by ether, giving tetrahedral geometry to magnesium. So, widely used for the formation of carbon-carbon bonds in organic synthesis. Okay. And these compounds, Grignard reagents, are very similar to organolithiums in terms of their reactivity towards other halides to form carbon-carbon bonds. And in case of Grignard reagent, one has to carry out the reaction in a polar solvent such as diethyl ether. That diethyl ether will give essentially a tetrahedral geometry through coordination of oxygen to magnesium in this fashion. So, in absence of any interaction or association, if you prepare Grignard reagents such as RMgCl that essentially get coordinated with the two equivalents of ether to have a tetrahedral geometry, and this one will give temporarily coordinative saturation to magnesium and it stabilizes this Grignard reagents. That is the reason the solvent is very important, and one has to choose a polar solvent while performing Grignard reaction to generate a species of the type RMgCl. The organometallic compounds of R2Mg are also known, but much less studied than the Grignard reagents. Both dimethyl beryllium and dimethyl magnesium have the polymeric structure similar to beryllium hydride or beryllium chloride. So, that I would show you later. How one can explain the polymeric structure using even as simple as valence bond concept. And about the utility of Grignard reagents in organic reactions, just I want to show you one reaction here. For example, take RMgCl and treat this with a ketone. Initially, it forms and this one under acidic condition forms the corresponding alcohol through the elimination of magnesium chloride. So, that means treatment of Grignard reagent to ketone leads to the formation of tertiary alcohol. Not only that one can also use in various other p block element organo compounds. For example, treatment of Grignard reagents such as ethyl magnesium bromide with PCl3 phosphorus trichloride leads to the formation of very important phosphine ligand trithylphosphine. So, one can use a variety of reagents of magnesium with general formula RMgX and use it extensively. One can extensively use it in organic chemistry or with p block elements to make element to carbon bonds. You can see here I have shown some structures of organomagnesium compounds here. They can have a dimeric structure. You can see here they can have dimeric structure with the two alkyl groups bridging, or one can also have trimeric structure like this, two such units bridging, or one can also have a cyclic structure in this fashion, or simply they can exist in monomeric form if the solvent is available to satisfy its coordinative saturation. And when we have this kind, they are essentially 3-centered 2-electron bonds. I will show you how 3-centered 2-electron bonds can be realized in case of beryllium carbon compounds or beryllium hydride compounds. I am taking here dimethyl beryllium compound. So, well, beryllium you have s2 electron, that is you have 2 electrons here and you have no electrons in p orbital. So, during the formation of compound, what we get is S and P together, they combine together to form 4 hybrid orbital after promoting this s electron to one of the p orbital, and now we have 4 sp3 orbitals with 2 having 1 electron and 2 having no electrons. So, now here something like this is there. So, that means I am considering a situation like this here. You have one here, one here. Now, another beryllium atom it comes. Now, basically what you have is, if you consider hydrogen, one can consider 1 s1 electron here, 1 s1 electron here, electron is not here. So, electron is here. So, now basically here no electron is there here, here 1 electron is there and this is 1 electron is there. So, 1, 2, 3, 3 centered 2 electron bond is formed, and same thing is true in case of here also. Here 1 electron is there, here no electron is there, and you have 3 centered 2 electron bonds. So, essentially you have 3 centered 2 electron bonds are. I would discuss more about these aspects when I go to group 13 elements and discussing the hydrates of boron. Okay. So, let us look into the uses of group 2 elements and their compounds. Beryllium is used in making alloys. For example, copper beryllium alloy used in making high strength springs. Metallic beryllium is used in making windows of X-ray tubes, and magnesium alloys with aluminum, zinc and tin are also used in a lot of materials, and magnesium alloy, because of its lighter and strength, used in aircraft construction, and magnesium powder and ribbon is also extensively used in flash powders, bulbs, incendiary bombs and signals. And suspension of magnesium hydroxide in water, that is called milk of magnesia, used in antacid. Magnesium carbonate is used in toothpaste, and calcium is used in extraction of metals from oxides, which are otherwise difficult to reduce with carbon. So, when you have some metals which are very difficult to be reduced from the corresponding metal oxides using carbon, one can comfortably conveniently use calcium. Of course, reactions has to be carried out at higher temperature, and calcium and beryllium metals, owing to their reactivity with oxygen and nitrogen at elevated temperature, used to remove a small quantity of air from vacuum tubes. For effective vacuum, it has to be thoroughly evacuated to remove the trace amount of air, and essentially air containing oxygen and nitrogen. So, since they have high affinity at very high temperature for oxygen and nitrogen, by purging at high temperature calcium and barium, one can conveniently eliminate all traces of oxygen and nitrogen to get pure vacuum, and then one can seal to generate vacuum tubes. So, radium salts are used in radiotherapy, that is in cancer treatment. So, now let us look into the diagonal relationship between beryllium and aluminum. If you just look into the ionic radius of beryllium 2 plus, that is about 31 picometer, and charge to size ratio is very high, and that can be compared to the size of aluminum 3 plus. Since both of them have very comparative or very similar ionic radius, you can anticipate similarities in their properties. Aluminum forms an oxide film and as a result resistant to acid attack, this is called passivation, and beryllium does the same, and once when pure beryllium is exposed, it immediately forms a thin coating of beryllium oxide, and that prevents from further oxidation, and even that can even prevent in the acid attack, or it can resist acid attack. So, beryllium hydroxide dissolves in alkali to form berylites, that is BeOH 4 times 2 minus. Aluminum does the same. So, aluminum also under strong alkaline condition, aluminum trihydroxide which is insoluble forms aluminum tetrahydroxide, that is soluble, and chlorides of both beryllium and aluminum have bridged structure. If you look into aluminum trichloride, that is dimeric, having 2 chloro bridges having the composition Al2Cl6, and similarly beryllium dichloride is also unstable, it undergoes dimerization to form Be2Cl4, or it can have a polymeric network. Chlorides of both beryllium and aluminum have bridged structures, and of course, both are used in Fadel-Crafts reaction for making CC bonds, and both have strong tendency to form complexes, that is beryllium F4 2 minus and also hexafluoroaluminate 3 minus. Now, let us look into few questions like suggest a structure for dimer of BeCl2 and explain how its formation illustrates BeCl2 acting as a Lewis acid. So, the question is BeCl2 forms dimer. So, that means how you can evoke the acidic and basic properties or Lewis acidic property of BeCl2 that can facilitate the bridging formation or facilitation of the dimeric or one dimensional chain structure. The next another question I will be answering that one shortly. Why does the solubility of alkaline earth metal hydroxides in water increases down the group? So, first let us look into, one can write BeCl like this. So, now as I mentioned here, if beryllium has undergone sp3 hybridization, we have 4 sp3 hybrid orbitals are there. Out of that one, 2 sp3 have 1 electron each and 2 sp3 do not have any electron, and those which have 1 electron can combine with Cl to form 2 BCl bonds, other ones are empty. Now, another beryllium is there. In the same way I can write the situation is same here. So, now this chlorine has, if you just remember or recall the Lewis dot structure, it has 8 electrons are there and 2 electrons are participate in making BeCl bond. So, these electrons can be given here and this electron can be given here, and then this repeats. So, because of this one here, beryllium acts as a Lewis acid and takes 2 electrons from beryllium, and in that fashion one beryllium, when it is acting as Lewis acid, this beryllium acts as a Lewis base, and when you go to the next one, so that means basically there is a tandemness is there in its behavior acting as Lewis acid and Lewis base, that results in the formation of this bridging bonds, eventually that leads to the formation of a one dimensional chain. So, this is how one can explain the Lewis acidity of beryllium that leads to the formation of one dimensional chain. And why does the solubility of alkaline earth metal hydroxide in water increases down the group? That means, among alkali earth metal hydroxides, the ion being common, the cationic radius will influence the lattice enthalpy. Since the lattice enthalpy decreases much more than the hydration enthalpy, with increasing ionic size, the solubility increases as we go down the group. And then if you look again, why does the solubility of alkaline earth metal carbonates and sulfates in water decreases down the group? In fact, barium carbonate highly insoluble and it is stable, it does not decompose readily. The size of anions being much larger compared to cations, the lattice enthalpy will remain almost constant within a particular group. Since the hydration enthalpy decreases down the group, solubility will increase as found for alkaline earth metal carbonates and sulfates. So, next the question, if I go back to this one, there is a question here reaction of magnesium carbide with water gives propane. So, just look into the question carefully. Reaction of a magnesium carbide with water gives propane. Suggest a formulation of the carbide and give an example of a common gaseous molecule with which the carbide ion is isoelectronic. That means, if the statement given clearly states that there is a magnesium carbide and which on treatment with water gives propane. Propane means there should be 3 carbons. If 3 carbons are there and magnesium carbide is there, one can think of Mg2C3 because propane is there. And then if it is giving, so what kind of reaction you can see, what kind of binding can be anticipated here. So, if it gives propane, it should be something like this. This is propane. Okay. So, one can now write and complete the reaction. So, now if you just see this equation is balanced now. So, Mg2C3 plus 2H2O gives CH3C triple bond CH 2MgO. So, now that means this one can write okay. So, suggest a formulation of the carbide. So, carbide is Mg2C3 and this is isoelectronic with carbon dioxide. So, just by analyzing this statement one can conveniently write the right equation and arrive at the right answer. So, with this I complete the chemistry of alkaline earth metals. In my next lecture I would be discussing about group 13 elements, that is the boron group. So, we have in group 13 we have boron, aluminum, gallium, indium and thallium. So, I shall discuss the chemistry of those in my next lecture. So, let me summarize the salient features of the group 2 elements. In case of group 2 elements, +2 oxygen state dominates the chemistry of group 2 elements. So, in case of group 2 elements +2 oxygen state dominates, all alkaline earth metals show very low first and second ionization enthalpies and are most electropositive elements in the periodic table. So, beryllium 2 plus due to its very small size forms either covalent compounds or contain solvented ions. These features are not seen with the rest of the elements. The group 2 metals form more stable coordination complexes compared to the group 1 metals, and alkaline earth metals form basic oxides with beryllium due to its smaller size. Beryllium oxide is amphoteric, that means all alkaline earth metals form basic oxides except beryllium. In case of beryllium, due to its smaller size, BeO acts as an amphoteric oxide, very similar to aluminum oxide. So, this completes the discussion on the chemistry of group 2 elements. In my next lecture, I will be discussing on the group 13 elements starting from boron and aluminum, gallium, indium and thallium. So, thank you very much.